Okay, this video is on A2, investigating the concept of a derivative. Okay, so I thought I better give you a rundown of everything that's in A2. So what we have is, first we want to understand what a derivative is. What does this word mean? So we kind of covered that in the first video of A2. And then we want to understand like what graphs of functions and their derivative looks like. So if you saw a function, you would know what its derivative graph would look like. Or just other simple things like if you saw a function like a quadratic, would you be able to describe the rate of change at each kind of interval in on the quadratic? Like for example, here you know it would have a positive slope, here it would have a negative slope, and right here it would have a zero slope. So like that kind of thing. Also, we need to be able to compute derivatives from first principles, and we're focusing on polynomials for that. So first principles is the thing we also learned in the first video, which is the limit as h goes to 0, that whole equation. And then finally, the last thing is we want to determine derivatives of sinusoidal and exponential functions. And that is A2. And then A3 is going to bring us to all of the derivative rules. Okay, so in this video, I'm going to talk about, we're going to hit on this again. So we're going to do more first principle stuff because it's good to practice that a lot. And then we're also going to just try to connect some graphing things. And I feel like every video is going to talk about derivatives, so hopefully it'll contribute to your understanding. Okay, that's the plan. So let's start with the word problem. Okay, so word problem you could see in grade 10 even. So the height of a javelin tossed into the air is modeled by this equation. Height's meters and time is seconds. So we want to determine the rate of change of the height of the javelin at time t, and we're going to express the derivative using Leibniz notation. Okay, so basically we're going to use first principles to find the derivative. That's what we're doing, because the derivative will find us the rate of change at every point on the graph. Okay, so if we're using Leibniz notation, then we're going to write that as dh by dt. The change in height with respect to time. And we're going to find the limit as h goes to 0 of, instead of f, I'm going to use the h because that's what this is, of t instead of x plus h minus h of t, and the whole thing is divided by h. So I just replaced, like, normally it was like f of x plus h minus f of x. So I just replaced the x with t's, and the f became the capital H for height. Okay, so same formula. Okay, so you know how normally I like to just calculate these two things before I start? Okay, so we already know what h of t is. It's just this. And then we need h of t plus h. So let's just calculate that off to the side here. So h of t plus h is going to be equal to, basically everywhere you see a t in that expression, you're going to add a t plus h. So we got negative 4.9 t plus h squared plus 10 t plus h plus 1. So all I did was everywhere I saw a t, I just changed it to a t plus h, and I had to put it in brackets. Now I'm just going to expand all of that. Sorry, I'm just going to move my equal sign back here because I think I'll need the space. Okay, so negative 4.9, and then we know t plus h squared is going to be t squared plus 2th plus h squared. And then I'm just going to distributive property this, so I'll get 10t plus 10h plus 1. Okay, now I'm just going to distributive property the negative 4.9 t squared, and then negative 4.9 times 2 will be negative 9.8 th minus 4.9 h squared plus 10t plus 10h plus 1. Okay, that's a lot of stuff. I guess that's all I can do. Okay, awesome. That's a lot of stuff. Okay. Sorry, I'm just gonna move this over. Okay, sorry. So, okay, we're gonna sub this whole entire thing in for h of t plus h. So it will be negative 4.9 t squared minus 9.8 th minus 4.9 h squared. I gotta get rid of that line. Plus 10t plus 10h plus 1. Okay, that's just for our first one. Now we need h of t, which is just the original equation. So minus 4.9 t squared. Oh, P.S. Since we're minusing that entire equation, I'm just going to put it in brackets because that negative is going to get applied to the whole thing. Okay. Also, I forgot to write the limit part. Amateur. Okay, and then the whole thing is divided by h. Okay, cool. So let's keep going. Okay, so what happens with this, since we're minusing that whole thing, is all of those guys just turn to the opposite sign. So that'll become plus, that will become, and those guys will become minus. Okay, so now let's just collect like terms. So the minus 4.9 t squareds go away because you have a minus and a plus. The 10 t's go away. The 1's go away. And we're just left with basically everything that still has an h in it. So we're left with this guy has an h, this guy has a couple of h's, and that guy has an h. So I'm just going to go ahead and factor an h right away. And then we have negative 9.8t minus 4.9h plus 10. And divided by h, so the h's can cancel out. And now we're left with negative 9.8t minus 4.9h plus 10. And now if I just replace the h with 0, sub a 0 in for h, that guy's going to go away. So I'm just left with negative 9.8t plus 10, which is what dh by dt is equal to. So that is our rate of change of the height of the javelin at time t. This guy right here. Or in other words, that's the derivative of our quadratic expression. Okay, awesome. So we did part A. That is the answer. And for part B, it asks us to determine the rate of change of the javelin after 3 seconds. So to do that, sometimes people use this kind of notation. They use like dh by dt. And then they put this line here. And they say when t is equal to 3. So just kind of shows what you're subbing in. I'm not picky. You don't have to do that. So negative 9.8 times 3 plus 10 is equal to negative 19.4. And what that would mean is that would be the instantaneous rate of change of the height of the javelin at 3 seconds. So it would be like meters per second. So that's how fast the javelin is traveling after 3 seconds. Awesome. Okay. Next question. Okay, let's try to find the derivative of y equals 1 over x. So I know this is a rational function, but I think it would be good to try it using our first principles. Okay, So we're going to find the derivative of 1 over h, or 1 over x, sorry. Okay, so we're differentiating, so we're going to do dy by dx, the change in y with respect to x, of the limit as h goes to 0, of f of x plus h minus f of x, and then the whole thing is divided by h. Okay, so let's sub in stuff. I'm not going to do this over to the side because we only have 1x, so it's pretty easy. So 1 over x is what f of x stands for. And f of x plus h, you're just going to stick an x plus h in the denominator. And then minus f of x, which is 1 over x, all divided by h. Okay, awesome. So we just have a little bit of fraction work to do here. So, what should we do? I'm thinking we want common denominators on top. That seems like something that would be good. So, it's hard to change any of these because they're all variables. So we're actually just going to give each other's denominator. So 1 over x plus h, I'm going to multiply top and bottom by x. So I'm going to multiply the top by x, and I'm going to multiply the bottom by x, because then it's actually like I'm just multiplying that fraction by 1. So that's purely just so I can have a common denominator. And then this guy, I'm actually going to multiply the top and bottom by x plus h, because then I'm actually just multiplying it by 1, but I'm going to get the denominators to be the same. And the whole thing is divided by h. Okay, so now our denominator is going to be x times x plus h. And in my first fraction, my numerator is 1 times x, so it'll just be x minus. And my other one will be 1 times x plus h, which is x plus h, over x times x plus h. And the whole thing is divided by h. Okay, so I'm just going to keep going. Limit as h goes to 0. Don't think about canceling because that would be ridiculous. You just put it there. And you did it so that you could have a common denominator of x, x plus h, and then your numerator is now, look what happens, x minus x plus 8. Oh, just kidding. It wouldn't be plus h. It would be minus h, because that minus sign gets applied to both terms. Okay, and then the whole thing's divided by h. Okay, so limit as h goes to 0. So x minus x is gone. And I'm going to change this. So you know when you divide fractions, you can change this guy to a multiplication. And then you have to flip that fraction. So this will become negative h over x times x plus h. Now I'm going to change this guy to a multiplying, and I'm going to change h to 1 over h. So that's just how we divide fractions. So now my h's can actually cancel out, which is perfect. That's what I wanted to happen. And now I'm just left with a negative 1 in my numerator and an x times x plus h in my denominator. So now if I sub 0 in for h, I will get negative 1 over x times x, which is x squared. So that is the derivative. So the derivative of 1 over x is negative 1 over x squared. So our original function was 1 over x, and then our derivative is negative 1 over x squared. Awesome. And just a couple things to note. So we know 1 over x is a rational function. So what's interesting about derivatives is they could not exist in some places. So we know the graph of 1 over x is this guy. So we graphed it in grade 11 and in grade 12. So it's got two asymptotes. It has a vertical asymptote here and a horizontal one here. So our function doesn't exist at x equals 0. There's nothing there because there's an asymptote there. So what you'll notice about the derivative is, if you were to graph the derivative, I believe it's going to look like, I don't know, it's going to look something like this, I believe. negative 1 over x squared. I'm sorry if I'm wrong, but I think it's going to look something like that. I definitely know it's going to have an asymptote at x equals 0. Because you know how I can tell is because if I subbed 0 in for x, I would get an undefined answer there. So I know that the derivative and the function doesn't... I don't know if I should say doesn't exist, or it's, maybe that's like a weird way to say it. I think I would say the function is non-differentiable. Differentiable. At x equals 0. So you can't take the derivative at x equals 0. Because your function doesn't even exist there. So that totally makes sense. Okay, just while we're on this topic too, there's other spots that you can't differentiate a function at. Just gonna write this, sorry. Differentiable. No derivatives. Derivative exists in some cases. So we just showed one where if the function doesn't exist there and then the derivative doesn't either, then you can't differentiate it at that point. So there's also these other situations, and it kind of like relates back to our limits chat. So there's 3 cases that we're just gonna look at. So one is I don't know, I guess we could say it in 2 different ways, like a cusp. So it kind of looks like that. So you can't differentiate a function right at that cusp because there's the slopes of those tangents that are approaching the cusp don't approach the same value. So if you were to draw a tangent at that cusp, it wouldn't be like it. Like there's many different options for a tangent line at that cusp. So it's not differentiable here. Also, vertical asymptotes or vertical tangent lines aren't differentiable. So like even if you had a function that went like this, here you've got, you would have, like we're probably not going to look at functions like that, but if you were to draw a tangent at this point, it would be a vertical line, which is undefined. So like we'll call this one a cusp. You can't differentiate it. We'll call this, if you end up with a vertical tangent, it's not going to be differentiable. Differentiable? Okay, sorry. And if there's any discontinuity in your graph, you're not going to be able to find the derivative of the function. So you know those piecewise functions that we have, like this, you're not going to be able to calculate the derivative whenever it's discontinuous. Also, in addition to a cusp is like a corner piece, like I don't know what you call that, I guess like a corner. You won't be able to differentiate it at that either. Maybe that would be called like a corner. So all of these spots on your graph, you wouldn't be able to find the derivative of them. Like you'd be able to calculate the derivative of, you know, these parts of the graph, that's fine. But just at this one particular point, you wouldn't be able to find the derivative. Okay.